record. Okay, so last lecture was on this idea of analog and digital conversions, right? If you have some amplitude waves coming from like a microphone, such as the one I'm wearing on my head right now, and I'm making noise with, right? How do you convert that into digital signal that your computer can process and then send to Zoom and then upload to Canvas so you can actually listen to my voice, right? Similarly, you know, if you have a camera, right? A camera detects light level, right? So it actually detects, well, for visible spectrum, we only care about red, blue, and green. So it actually detects 3 different wavelengths of light. And those levels are analog signals, right? In order for you to convert to digital, right? You have to do this analog to digital conversion, which we talked about last time, but we did the most expensive kind, right? What was that called? Anyone remember what it was called? I'm sorry? Flash ADC, right? We can even see a picture of it, right? Let's go up here, right? Right. This is kind of a schematic of a flash ADC, right? Where it's expensive because in order for you to do, you know, let's say 8-bit conversion, you're gonna need 255 resistor, 255 comparator, 255 XOR gate, and as I said, a crap load of diodes that I don't even want to count, right? So these things get very expensive very quickly. What we're gonna do today, we're gonna do the cheap version of it. Well, let's see, the more economical version of it. But before we can talk about successive approximation ADC, what we need to do is we're going to have to teach you guys how do you do the opposite, where you're converting a digital signal into analog. So let's say you have a bunch of ones and zeros, right? How do you convert that back to analog? So going the other way, okay? So this is actually something we kind of already learned about. So digital to analog conversion is just basically an op-amp circuit, okay? So if you look at this little circuit here, right? The digital signal will come in here, okay? And let's say the digital 1 is represented by a voltage of 5 volts, right? So if this is 5 volts, then that means we're putting in 1. If this is 0 volt, we're putting in 0. If this is 5 volt, we're putting in 1. So putting in 1, 0, 1 here, right? And these resistors are, let's say, multiplication of each other in order for the output to be actually scaled by the same, to be proportional to the significance of each of these bits. So D1 is the least significant bit, the LSB. Okay, hopefully that's going to be correct. Okay, and then in this case, you know, this is the 1's bit, this is the 2's bit, and this is going to be the 4's bit. Okay, this is going to be the most significant bit in this case. Okay, so whatever signal that comes in here, right, should be 4 times bigger. Well, it has the 4 times as big of an effect on the output of the op amp as the least significant bit. Does that make sense? That's why. So if you have 101 coming in here, right? This should give you something that's 4 times bigger than this one. And we're going to see why this happens because, or if you already kind of, I think a lot of you guys probably forgot how op amps work, right? The idea of an op amp is that whatever current flows through here, right? The ratio between the feedback resistor divided by the input resistor is the amplification, right? The or the gain, right? The gain equals to RF over RN, right? Okay. In this case, right, RF is the same amongst all 3 channels, right? But RN is 4 times bigger on the least significant bit. And the most significant bit has the, whatever R is, like, let's say it's 1K, and then this one would be 4K, right? So you can see that this channel has 4 times the gain compared to this one, right? And that's basically how we're going to do this analog to digital conversion. Sorry. digital to analog conversion. Sorry, wrong way. Okay. So let's see how this turns out. Okay. So let's say my inputs are 0, 0, 0, right? D1 is 0, D2 is 0, D3 is 0. Okay. Right. And we're assuming that digital 1 is represented by 5 volts in the circuit. Okay. Just good number. Okay. And then the let's make R equals to 1 kilo ohm. Right, just easy math because we just have to divide by 1,000. Okay, well, if all these voltages are 0, right, there's going to be no current going through any of these lines, right? So nothing happens. So all the currents are 0. That means the current through the feedback loop is also 0, and therefore the output is actually 0. Right? I'm not going to do all 8 of them. So we're just going to do maybe pick a couple of them. So let's say D1 is actually high, right? That means right here at this point is actually 5 volts, okay? Okay. What's going to happen is that, remember what an op amp is going to do? It's going to try to make the negative input and the positive input to be the same, right? So therefore, since the positive input is held to ground, this also has to be ground, right? It has to be 0 volt, okay? So we can actually calculate how much current is going to flow through that because you have 5 volts, you have 0, right? Right. And then the current through a resistor is the voltage divided by the resistance. The voltage change divided by resistance, just Ohm's law, divided by the resistance. And since the voltage change is 5 volts, the resistor we have is 4 kilo ohm, right? We're going to get 1.25 milliamp of current. Okay. Let's do this in milliamps. Okay. The rest are also 0, so they stay the same. Since the other rule of op amp is that the current cannot go into any of these inputs, right? Since there's a current of 1.25 milliamp going in here, it has to go through the feedback loop, right? So therefore, the feedback loop's current is also 1.25 milliamp, okay? But since you have a different resistor here, right? V out is going to be whatever that resistance is, right? Oops, well, V equals IR, not V equals I divided by R, or R divided by 5 times 1.25 milliamp. Might as well fill in the 1K ohm resistor here, okay? The K ohm and the milliamp cancel each other out. So this will give you 1 volt as the output, right? Remember that D1 is the 1's bit, right? When it flips from 0 to 1 volt, meaning it's flipping from digital 0 to digital 1, right? We get 1 as the input and 1 as the output, okay? Does that make sense? So, right? Because this is actually 1, right? Let's pick another one. We don't want to do all 7 of them. Do you want to do the last row just to see if it works the same? Right, the last row, right? This is representing 4 plus 2 plus 1, right? So the output hopefully is going to be around 7. We'll see if this is the case, right? Similarly, okay, I1 is basically the same because we have the same voltage here, 1.25 milliamp, okay? But I2 and I3 are now going to be non-zero, right? So I2, right, is going to be 5 volts divided by this resistor value instead. That resistor value is 2K, okay? This will give you 2.5 milliamp, okay? I3, right, is the current going through here, okay? It's still 5 volts divided by 1 kilo ohm instead. That's 5 milliamp, okay? So let's fill this in, 2.5, 5 milliamp, okay? Same rule that obeys by the op amp is that the input terminals collects no current, right? Current cannot go in there. So all 3 of these current 1, 2, 3, right, has to go through the feedback loop. So you have to add them all up. Whatever that number is, is going to be 8.75 milliamp. Hopefully I did that right. Okay. So therefore, V out is going to be, well, 4/5 times 1K, because that's the resistor value, times whatever that current is. And now this is where my math breaks down, right? I'm not going to be able to do that calculation in my head. Hopefully it comes out as almost close to 7. Times 8.75. What do you know? You get 7 volts. Pretty cool. Okay. Hopefully this circuit makes sense, right? I know it's been a while since we dealt with op amps, but there's only 2 rules you need to know about op amps, right? The input terminal has to be the same, and there's no current going into them, okay? So, there are other ways to do this, because this particular circuit relies on you having a 1K ohm, 2K, 4K, and whatever the heck this is, right? 800 ohm resistor, right? They all have to be exactly that value. There are other architecture you can do. This is known as a R2R ladder, where instead of, let's say you're trying to do it like an 8-bit digital to analog conversion, right? You actually need 9 different resistors that has the exact right value, right? And as you see in the lab, you don't have 8 different kinds of resistors usually, right? So what this allows you to do is actually only have basically like 3 different resistor value. You have ones that are set up to be twice the amount. You have one that is, the normal amount. So this 2R, right? And then the R here. And what happened is that you do need a resistor that kind of scales everything so that the output comes out to be correct, okay? And usually this factor is basically the 2 to the n bits. And I think this 5, where does this 5 come from? This 5 comes from the fact that there's 3. There's probably a way to calculate that, okay? But this is known as an R2R ladder. The analysis get a little bit more complicated. And I think just for the sake that we don't want to do we just want to do it? Okay, let's just do it, okay? Okay, so how does this circuit work, okay? Okay, you have some resistors here that's 2 times the value up here. And so all the vertical ones are 2 times, and then all the horizontal ones are 1 time. And then you have some scaling here also, okay? So what we do is we go back to, when was this? This is lab 1. We do this thing called the Thevenin's equivalent, okay? What this Thevenin's equivalent tells you is that if you have 2 resistors like this, right, you can combine them together, okay? When you combine them together, right, you have to figure out what R Thevenin is, okay? R Thevenin's. So we're trying to simplify this circuit, right, by just taking this piece and making 2 components into 1 component, okay? So remember, this thing has a 5-volt power supply up here, and down here is ground, right? Okay. So our Thevenin's in here. Well, how do you think? Anyone remember how to do Thevenin's equivalent? That's the voltage divider. I think that's going to be correct in this case, but we want to just have like a, so to get Thevenin's equivalent, we need V Thevenin, which is the same as V of the output here. So this is V out, right? This is the thing that's actually connecting to the other part of the circuit, right? With open circuit, right? Well, with no load. Okay, I should actually look up what I actually say is, okay? So yeah, so as you say, this is actually just a voltage divider. It'll also give you 2.5 volts, okay? Okay. R Thevenin is, if I do this math right, is V Thevenin divided by I short circuit. Remember that? Okay. I short circuit means, well, if you just connect this to ground, how much current will go through it? Okay. I short circuit, right, it's going to be 5 volts divided by 2 times what the resistor values are, right? So you can actually put that up here. VThev 5 volts. Well, VThev is 2.5. 2.5 volts. 5 volts divided by 2R. Okay. Do that right? Yeah. Okay. So on top, you have 1/2. You have, you've got fractions of fractions everywhere, right? This is 1/2 times 2R. Right? These actually cancel out. So R Thevenin is actually R. So when you redraw this circuit, okay? Yeah, this is not a very good diagram. When you redraw the circuit, you plug this back in here. Okay. Sorry. You plug this back in here. You have D1, D2, D3, right? You basically have whatever the voltage here is divided by 2 with 1 resistor. And then, but don't forget this one, okay? And the rest of the circuit is the same. R, right? Whatever that is, right? And these are just resistors in series, right? Resistors in series just adds. So when you combine those 2 resistors together, you get twice the resistance, right? You see how by doing the Thevenin's equivalent, you change this voltage to half of it, right? And if you keep doing this, okay, what will happen is that instead of VCC divided by 2, you get VCC divided by 4. And then on the last step, you're going to get VCC divided by 3. Okay, if you just go through all this Thevenin's equivalent analysis. Okay, so that means, right, if D1, which is this input up here, right, is equal to high, okay, what will happen is that the output is going to be 0.625 volts, which is going to be proportional to what the input is. Okay, so if, yeah, but then you get inverted. But since you're going through a inverting amplifier, okay, the output is going to be actually going to be -1 volts because of this. You know, we pick our resistor to be 8/5, whatever R2 is going to be. Okay. Okay. Then, if D2 is equal to high, then you get -2 volts. If D3 is high, then you get -4 volts. And this is basically the 1's bit, the 2's bit, and then the 4's bit. Okay. It's all negative, but that's okay, right? We can always flip this upside down. Okay. Right. And this is kind of nicer than the top design up here, which, you know, it makes a lot of sense, but it requires, you know, let's say you're trying to do like an 8-bit conversion, you're going to need 9 different resistors. That's the exact value, right? But this one, you always just need, basically, you need R, you need 2 times R, and you need something that's going to be like a potentiometer to scale this, okay? So you basically need 3 different resistors to do the digital to analog conversion. And for manufacturing reason, it's a lot easier to only have 3 different parts in your device versus having, like, you know, 8 different parts or 9 different parts. Okay. Okay. The analysis is more complicated, but then the actual implementation is simpler. Okay. So this is actually, I guess we don't have one of these. Have you guys seen what this is? You know what this is? Yeah, it's just HDMI to VGA adapter, right? HDMI, what's this D in HDMI stand for? I'm sorry? Digital. VGA is, well, I don't think the A stands for analog, but right? This is a digital to analog converter, right? So it takes digital signal, it goes through a little chip in there, just like that little R2 R ladder, and basically convert whatever digital signal into analog so that your old crappy screen can still see it, okay? Maybe not crappy. VGA monitors are still fine. They work, okay? And these are kind of cool. You can even look at like the circuit diagram for them, okay? You have the HDMI input here. It has to get decoded, okay? A lot of them also have an audio decoder, but that's a separate channel, okay? And what it does with the digital image signal, it does the digital to analog conversion and gives you the analog RGB image for your VGA monitor, okay? So these are, pretty cheap to make, right? It's just basically one op amp and a bunch of resistors, okay? Okay. All right, the reason we're talking about this, sorry about that, is so we can actually do analog to digital conversion, right? Well, analog to digital conversion without using flash ADCs, which is the very expensive one, right? So the analog and digital converter in my phone, the reason I need it, right, is because the cell signal is analog, right? I have to convert that information to digital. Well, the microphone is also analog, right? You have to convert that to digital, okay? So in these non-extreme type of applications, your phone, your TV, any consumer electronics, you don't need to do the analog to digital conversion within a nanosecond, right? Remember last time we were talking about, well, if the analog to digital conversion slows down your missile correction course by a nanosecond, you can miss a target by 10 miles. So in these non-military, non-extreme applications, it's okay to be slower, right? That's the point, okay? The algorithm is actually based on a binary search algorithm. This is actually known as, it's called binary search. So those of you with programming experience might have heard about this already. If you don't, we'll just describe it, okay? The method is being used is going to be called Successive Approximation Register, SAR, okay? So if you see an SAR in some device, that's the type of analog to digital conversion they're doing, okay? So let's do a 4-bit example here, okay? Where the analog input can be somewhere between 0 to 15 volts, okay? It's just somewhere between that, okay? Okay, the idea is that, let's say your input is 9 in decimal, okay? You need to convert that to digital. In digital, it's actually 1001, okay? When you do the successive approximation register approximation, you basically do series of guesses, okay? Right? So the first guess, what you're gonna do is you're gonna flip the highest bit, the most significant bit, okay? This represents the value of 8, right? 1000. How many zeros? 1000, yeah, right? Because this is the ones bit. Stop moving around. This is the ones bit, this is the twos, this is the fours, this is the 8s bit, right? Since the 8 bits has a value of 1, it represents a value of 8, okay? Well, 8 is not 9, right? So that's a really bad guess. Well, we'll see how this turns out, okay? What we're gonna do is we're gonna compare this number 8 to number 9, okay? Number 9 is bigger than 8. So therefore, we know our answer has to be bigger, right? It's not 8, but it has to be bigger than 8. So what we're gonna do, we're gonna go to the next bit and increase that value by increase the next most significant bit by 1, okay? Meaning I'm gonna flip this 0 to 1, okay? Okay, so this value is 12, right? Once again, I'm gonna compare 12 to 9, and I can do this using just a comparator, right? On an analog device, okay? Well, 12 is bigger than 9, so now I know my answer has to be less than 12. So it's somewhere between 8 and 12, right? Now I know what the range of the answer is. Since I know it has to be smaller, instead of just increasing this bit, I'm gonna shift this bit over by 1, okay? And those of you who finished the shift register lab, right, knows how to do this now, right? You can shift this over by 1. Now, instead of representing a value of 12, it represents a value of 10, right? Once again, we're going to compare 10 to 9 and say, well, 10 is bigger than 9. So in that case, what I'm going to do is I'm going to shift this again. So whenever the number is smaller, my number is smaller than the input, I add to the input. Sorry, I add to the approximation. Whenever my approximation is bigger than the input, I shift instead. So this is something you can do systematically, right? Because when you're circuit, you have to do everything by these systematic rules, okay? So once again, I shift that bit over. Then I get 1, 0, 0, 1. And that's actually equal to 7, okay? Then I'm going to do one more comparison, compare 7 to 9, right? Okay. And of course, 7 is less than 9. So instead of shifting, I'm going to add, right? So instead of shifting, I'm going to add. No, this is wrong. I didn't do that calculation right. I shift this over. This is actually value 9, right? Okay. So in this case, these two numbers are actually exactly the same. Depending on which one is slightly bigger or smaller, the comparator is going to either flip high or low, but it doesn't actually matter. Sorry. So actually it gets to the answer in 3 rounds. Okay. So then the thing to note is that this took 1 clock cycle because we're doing one comparison, 2 clock cycles, 3 clock cycles, 4 clock cycles, and then you get to the answer, right? It took 4 clock cycles to do one successive approximation analog to digital conversion. Okay, so it took 4 turns instead. Okay, remember flashed ADC can do it all in 1 turn. Okay, so this is already 4 times slower and we're only doing 4-bit conversion. Okay, it's actually worse than that. Okay, so if you do 64-bit conversion, it'll take 64 steps instead. Okay, it's not too bad, but eventually there are other things that in these successive approximation ADC you have to account for, not just this comparison stuff, right? Compare, right? The other thing you have to think about is that, okay, this is actually the schematic for the ADC you're going to actually use in the lab. Okay, okay, this is, where is it? The input is placed in here. This thing over here is called a sample and hold. It's not shipping and handling, but we'll talk about what that is in a second. Okay. Remember when we're doing the approximation, we're always comparing the two, right? Comparing our guess to what the input is. If it's bigger, then we increase the value. If it's smaller, if the input is smaller, right, then we shift, right? That determines what we do, okay? So this comparator actually determines what this thing called the successive approximation register actually do, okay? And this approximation, depending on what the comparator tells us to do, either shifts the bit or increase the bits, okay? And it gives it the next answer, right? And this is where the digital to analog conversion happens, right? That's why we have to talk about that first, okay? And then it sends that digital, it sends that analog signal out to here to the comparator. So every time it just kind of churns around and just compare until the end of conversion. Okay, this is called EOC. Okay. So, yeah, I think we already kind of did this. So I guess I could have just read through this instead. Okay. So we made 4 guesses, right, to do the 4-bit conversion. Okay. But each guess is actually not a single clock cycle. Okay. The reason is that when we guess, each time we guess, it took 1 clock cycle just to set the value of the, it took 1 cycle to do this part, took 1 cycle to do this part, took 1 cycle to do this part, right? There's actually more than 1 cycle in order to do each of these steps, okay? Note that here that, you know, to do the 4-bit conversion, it actually took 7 steps, okay? So one of the things that happen is that when you do successive approximation registry analog to digital conversion, right, it's going to slow down the conversion quite a bit, okay? But since, you know, you're not trying to track missiles with your phone, right, it's okay for this kind of process to be slower, okay? Let's see. Yeah. So it usually takes about 4 to 8 clock cycles per bit in order for you to do the approximation, okay? So for example, if you were doing a 4-bit conversion, actually it takes about 16 to 25 cycles. To do 8-bit conversion, which is the actual chip we have in our lab, it actually takes about 32 to 50 cycles for you to do the approximation, okay? There are even other things on top of it. We haven't talked about the sample and hold yet. That also takes some additional cycles, okay? There's also the end of conversion signals. You have to tell, you know, whatever you're sending the signal out to, oh, I'm done with this conversion, right? I'm ready. The digital signal is now ready to be read out. So read out all the digital binary numbers, and then it has to clear that registry, right? That'll take an extra cycle in order for that to happen, okay? So these little chips cost about $10. So if you were to do like an 8-bit conversion, it'll probably cost about 500 if you did it with flash ADCs, right? So this is cheap and also fits on your phone, okay? The chip we actually have actually does the 8-bit conversion in 66 cycles. And that's probably about the number you should be expecting, not 32, okay? I mean, I think you could design something that are like, can do it in 40 cycles, but that's gonna be pushing the limits quite a bit, okay? It's a complicated integrated circuit. It's a complicated chip. So it's always good to look at the data sheet. So usually in this lab, I will just have you guys look up data sheets and stuff like that. But since we're not doing pre-lab for this lab, we're not going to do that. So, so this doesn't. So this is this data sheet for ADC 080, and the X here means that it's just unknown. Okay, we're using the 805. You could buy the 804, 803, 802, 801. I think those are just the previous generations of it. It's just the higher number, the newer it is. Okay. Right. And it's an analog to digital converter. I don't actually know what micro P means. But there's all the different specification for it. Okay. It works with 2.5 volt reference voltage. That means you want the analog input to be centered around 2.5 volts. Okay, and that the lab actually tells you to do that. Okay. The other thing to note is that there's the conversion time. Okay. So minimum, maximum. So I don't know why they didn't type in the typical. It's just somewhere between these two numbers, right? It takes about 100 microseconds for it to do one conversion. Okay, so that's how long it takes for it. That's as fast as you can convert. Okay. As you see here, right, the number of clock cycles it takes to do a conversion is about 66. It can. That's actually the minimum. That's the fastest it can go. You should not expect it to go faster than 73. Okay, so and the clock frequency you can run it at is, you know, from 100 kilohertz to 1.5 megahertz. Okay, so it has a pretty broad range on that. Okay, and you can do, you know, 9,000 to 9,700 conversions per second. Okay, you know, still a lot faster than I can do, right? It's not that fast, but it's going to be good enough. Okay, so this is the pinout information. So this is, you can see this in the lab. It's a really big chip. It's the longest chip you have in your kit. Okay, and that's because you have a bunch of setting here. You also have the clock that's going to be the input, right? And then you have V in, right? So typically V minus will probably be ground, and this will be the positive input on your function generator or whatever you're inputting. V ref divided by 2, you want this to set this to 2.5 volts, right? Using a voltage divider, okay? And then all the stuff on the right-hand side is actually all the outputs. So this is the least significant bit. This is the most significant bit. I think in the lab, it just has you do 4, right, Dylan? You only have to do 4. You don't have to do all 8, right? Yeah, when you do when you do the most significant 4, it just gives you a 4-bit conversion instead of a 8-bit conversion. You could hook up all 8, but it just gets kind of messy at that point. It also has an internal clock. Okay, I'll show you how to actually hook up the internal clock. Internal clock can be set up with this little example here, right? So in case you don't have an external function generator that gives you a clock, the chip itself inside it has a clock. It also, so if you hook this clock R, which is pin 19, and then clock in, which is pin 4, it's very confusing. They're actually nowhere near each other, right? But the diagram just tells you how to connect things. If you put a 10K ohm resistor here, right? Connecting these 2 lines together, and then taking that line to ground through a 150 picofarad capacitor, you can calculate the clock frequency by just taking 1 over 2 pi, the RC value, right? Remember that omega is 1 over RC, right? And then F is just going to be omega over 2 pi, right? So this is actually 2 pi RC. Okay. You plug those numbers in, 10K, 100 pico, you get 100 kilohertz, okay? And that's how you can set the clock on your ADC chip as you like, okay? Don't try to go for, as noted up here, right? It could go up to 1.5 megahertz. Don't go beyond, 640 kilohertz, okay? Because what happens that when you go over a megahertz, the chip starts to get hot. You actually have to put heat sinks on it, and we don't have heat sinks, okay? All right, any questions about the ADC chips we'll be using? Okay, and how it works, right? Right, the shift register is like, maybe 10 transistors, right? And then the op amp, you have an op amp, you have a few resistors, right? As opposed to, in order to do this, right, on a flash ADC, you need 255 resistor, 255 comparator, right? So that's why this is a lot cheaper and smaller. What's the size comparator? Well, you can make like 255 op amp comparator onto a chip that's pretty small. But this is like the number of parts in the successive approximation ADCs is like 30, right? Where to do the flash ADC, right, you need like 255 plus 255, 255, and then a crap load of diodes. So like 1,000 parts, right? So there's the cost difference. And however you can shrink those things, right, that's the size, right? So probably the smallest successive approximation ADC you can make is going to be like 40 times smaller than the flash ADC, right? Just by the number of components. Okay. So one more thing before we need to move on into the lab. Notice that since we are doing this conversion much slower, okay, we need this little device called sample and hold, okay? It's actually up here. I can actually show you up here where we had this is the shipping and handling thing, okay? Sample and hold, okay? The reason we need a sample and hold is that it takes a while for this analog to digital conversion to happen, right? What you want to do, but if your signal is going up and down really fast, right? You're going to be changing your input while you're processing your output, right? So you want that input to be constant while you're doing the conversion, okay? And this is where a sample and hold chip is very useful. It's very simple, okay? It's basically an op amp, okay? Where it has an additional output to it that allows you to have what's known as a holding capacitor to basically hold the voltage that you tell it to do so, okay? So this is the little circuit diagram for it. You have the analog input, so whatever the input you want. you also have a logic input, okay? What the logic input does is that if the logic input is high, it'll basically pass whatever analog input is on the input and send it to the output, okay? But if the logic is low, it'll disconnect this, okay? And keep the output with a holding capacitor, okay? And this holding capacitor, unfortunately, since it's not, ideal, right? You can't have an ideal system. The voltage on this holding capacitor is going to decay over time. It's going to be known as the droop voltage, okay? The droop of the voltage. So this is another word that we learned in, I think, in lab 2, right? When we had this, the first alternating current lab, okay? Okay. So let's see. The other thing to note is that since we're dealing with transistors, okay, there's also diodes inside the sample and hold, okay? If you want to hold a voltage from, let's say, 0 to 5 volt, that's the range you're working with, you actually have to have negative 1.2 volts to 6.2 volts because of 2x the diode drop, okay? So these power supply here has to be 1.2 volts beyond the range of your input, okay? So if you go from 0 to 5, you have to go negative 1.2 to 6.2, okay? Go even a little bit further than that, like 7.5 or something, right? That way, it actually can hold the voltage that you want, okay? So the thing is, you're picking this holding capacitor, and that holding capacitor is going to be customized to the applications that you're dealing with, okay? I think the lab is going to have you play around with a few of them, okay? So there's two different competing specification you have to deal with when you're picking this holding capacitor. First is the acquisition time. The acquisition time tells you once the logic input goes high, how long does it take for the analog input to be exactly approximately the same as the output, okay? How long does that take, okay? So let's look at this little diagram from the specification sheet, right? That's pretty old school, okay? So on the x-axis is the holding capacitor value, so 0.001 microfarad, so that's 1 nanofarad, 10 nanofarad, 100 nanofarad, and then 1,000 or 1 microfarad, right? Okay. This is the amount of time it takes, right, for the input you place in the sample and hold to be transmitted completely to the output, right? So there's two lines here. There's the 1%, and then there's a 0.01%. That means, right, if you want your answer to be, 0.1% of the difference between the input and output to be 0.1%, you use this line. If you want it to be more accurate, you use this line, right? So let's just use the less accurate line. So if I pick, let's say, a 100 nanofarad capacitor, right, it's going to take about 100 microseconds, okay? So that's already kind of slow, right? So if I pick a 1 nanofarad, right, it's going to take this weird scale, 1, 2, so that's 2, 3, 4, right? It's going to take 4 microseconds for the input of the sample and hold to be transmitted to the output of the sample and hold. Does that make sense? Okay, so you have to pick. So in this case, right, for acquisition time, you want to pick a small capacitor, right? But a small capacitor also loses its charge faster, right? Or percentage of its charge faster, right? And this is the droop rate, okay? What's plotted here is delta V over delta T, okay? Means how many volts do you lose per second, okay? Right? And down here, once again, is the different capacitor values you have, okay? If I pick the 100 nanofarad one at, let's say, 72 Celsius, around room temperature, right? You are going to lose 10 to the negative 9, 10 to the negative 4. Yeah, 10 to the negative 4 volts per second, okay? But if you pick a 1 nanofarad, you're going to lose a lot more. You're going to lose about 1/100th of a volt per second, which is a big deal, right? If you're losing, if your voltage is changing by 0.01 volt every second, that's going to drain basically your entire voltage in 60 seconds, right? Okay. Okay. So in this case, if you want a small drip rate, you have to pick a capacitor that's to the right. But if you want a fast acquisition time, you want to pick a capacitor to the left. So you have to compete two, and then you still have to pick the one in the middle to figure out what's best for you. Okay. Any questions about the sample and hold? Okay. We actually don't really need it because the FPGA BASI board has its own, so we don't actually have to deal with it too much. But if you're going to be going on to design data acquisition systems, which we're going to talk about on Monday, it's very important for you to know how to design things like this, okay? All right.